You want to go? Let's go over this. Yep. Real quick, this handout, just a little study guide. Name the two types of switch input electrical circuit designs, which is what? Pull up and pull down. This is all Chapter 2 material. And internally sourced. So I have in parentheses by the computer. An internally sourced switch input is called a what? Pull down. Very good. It's internally sourced. And so a review of that would be my computer. This is internal. We have a resistor and a source, and our switch would be external, of course, on either design, but the key being inside of the module is my source, externally grounded. This is a pull down design. Name at least 3 switch inputs used on engine, body, or transmission computer systems. That should say systems.
Throttle position, parking, camshaft.
Like key fob, door lock, or oil pressure?
Yeah, any switch that's on the car, if you guys remember. Anything that you can imagine inside of the car on today's cars would be a switch input.
There's a bunch of lists.
Yeah, there's a list on page 2 of the chapter. I had like park neutral, headlight switch, power steering pressure switch.
Now, does it matter if it's the hydraulic or mechanical or electric?
No.
No, I was asking.
It doesn't. Yeah, no, it doesn't matter at all. Because those are part of it too. So I want examples here, guys, is what I'm looking for. Everybody comfortable with that? Yeah, I heard cruise control back there. That would absolutely be acceptable in that. So pull down. So the next 2 questions, this will be good because this is where we left off yesterday talking about the wiring and testing of these. A pull down switch input reads high volts on both wires at the switch. Back probing with the switch closed, what is most likely the cause? So before you answer, one of the things that you would need to do is visualize the pull down circuit, which we have drawn right here. It's an open ground. So I'm telling you that what we're doing is we're closing the switch, which is important. In this measurement, switch is closed, and you're measuring both sides. What do I mean by both sides? We're measuring the signal wire, and we're measuring the ground wire, and I'm saying that we have high volts. So in our example, let's say we have 12 and 12. The only possible cause for that, you got an open in your ground circuit. Number 5, a pull down switch input reads 0 volts on both wires at the switch. Back probing all the time. So 0 volts all the time. I'm saying switch open or switch closed. We're reading 0 and 0. And I'm asking you to list at least 3 possibilities for this condition. And that would be, there's probably 4 or 5 that we could put on this list.
What? Short to ground on the signal wire?
Very good. Short to ground on the signal wire would be 1. Yes, an open signal wire would be another. Very good. PCM problem would be another. The computer's not sending out this reference voltage. Shorted switch would be another. That's 4. And the only other one would really be a connector problem, a pin contact problem. Very good. I'm impressed. You guys must have a good teacher. What type of signal, so number 6, what type of signal does a switch input make? Analog or digital? Digital. Yeah, it's an easy one. Digital. Then we're on to some Chapter 3 material. This is all from 7 up. So these would be Chapter 2, and these guys would be 3. We'll be getting to those later today. Chapter 3, I think, yeah, we should be able to get to Chapter 3 today. All right, we got some true-false ones here we can answer. Number 1, signal voltage on a pull-up type switch input should be low with the switch closed. And this would be one you have to visualize it to answer that question. A pull-up design circuit would be one where the switch has an external source, and internally there's a ground and a sensing circuit. That's pretty much it that's inside of there. And I'm saying that the signal voltage should be low with the switch closed. True or false? It's easy to answer when you can visualize the switch. That's a false statement. Because with the switch open, my voltage would be 0 volts, and the computer would see that too. Close the switch, and voltage should get pulled up. That's what it does. It's a pull-up design. It should be high with the switch closed. Okay. Signal voltage, this is number 2 now. Signal voltage on a pull down. So before you even answer the question in your mind, you want to visualize the pull down design. Internal resistor, internal source, sensing circuit would sit after the resistor, and I'm asking you with the switch closed, so my switch is closed, what is my voltage level going to be on the signal wire?
Low.
Yeah, it should be low. From here all the way out, this entire signal wire, of course the ground too, but the signal wire is what I'm asking about. It should be low. That is true for number 2. Switch input identification is the next one. I'm asking you to identify it with a voltmeter. And if you remember the 2 designs, we'll draw these again. This is the example. 12, 12, 12, 0, 0, 0, 12, 0.
What means 0, 12?
We're just looking at it backwards. I'm doing that intentionally. That's a good point. I'm doing that intentionally to make you think a little bit more. But can you see, like, this would be one design with it open and closed. I'm not showing you the switch, internal switch position. Here's the other design with the switch open and closed. Can you see that in both of these examples, we have one that looks the same? So what position identifies the circuit design?
The open. Well, whenever the circuit is
Closed.
closed. Yeah, closed.
Circuit design is able to be identified with a voltmeter when the switch closes, because when the switch is open, they look the same. They can look the same. So what I have circled in red would be an open position, okay? And it is the closed position that identifies that. Expand on this just for a minute. Review. Can you tell me which one's which in the...
Top one's pulled up, bottom one's pulled down.
Very good. Very good. See, you weren't even here. So you learned that from my recorded lectures in chapter 2. So that's a good lesson for you guys that miss a day, is do what Bryce did, which is take the initiative, and remember that I have on my premium channel in chapter 2 a whole bunch of these recordings already, and that's exactly what Bryce did and was able to answer that question without even being here. That's pretty awesome. Yeah, top picture is a pull. This one's a pull up. The top picture is a pull up design, and the bottom picture, this is a pull down. All right, one more question I want to ask you. Can you tell me which one the signal wire is? This is a review. We covered this yesterday, but it's good to hear it again. Can you tell me which one of the pull-up design up here? Let's start with that one. Which one's the signal wire?
12. The right.
Left or right?
Right.
Yes, it would be this side. The side that's changing would be the signal wire. Okay? And then the side that stayed the same, in my case, what wire would this be? This would be the power. That would be the power wire. Our control, when we use the term control, that would be with an output. So be careful with your terminology, and always correct you guys when you use the wrong one, just to keep your perspectives correct as we move forward. Okay? So yeah, what I have circled in blue would be the power feed, and then what I have in green would be my signal wire. Bottom picture.
Left.
Yeah, it's the left. Here, this one's my signal wire, and it's going from 12 to 0, and then the other wire would be what? What would this wire be?
Power. Ground.
Nope, it's not a power. It's a constant ground. It's a constant ground.
I have a question about
Yes.
that. So is the pull down a kind of like a ground side control?
Yes.
Pulled up is
Yes. So the comment, and I want to correct you too, because I hear this a lot, and it's going to get worse when we go through chapter 3. The comment is the ground side. Say again, one more time.
It's like the pull down more towards a ground side control.
Ground side controlled. So yes, we could say the pull down is a ground side control. You wouldn't be wrong thinking that, but there's a reason I want to correct you in that statement, because when we learn about chapter 3 and the computer controlling circuits, we're going to apply that terminology. I'm going to say to you, the computer's controlling the ground of this circuit. And so we don't want to use the term control on an input. And the reason I don't want you to use that is I don't want you getting your inputs and outputs confused. And so I don't like the term control when we're talking about an input for that reason.
Would regulate be a better word for it?
Yeah, you could use regulate if you wanted to. Your perspective is not wrong. I just don't like the terminology. You'll see why as we continue here. The chapter 3, Bryce will come back and visit this conversation again when I show you the chapter 3 material and why I don't like to use the term control on an input. Okay? Good question. All right, some of you might be thinking, why did I draw it that way? That's awfully confusing. Well, on the car, you're not going to see this when you're working on the car. In your mind, you want to see this. Okay? This would be 12 and 0. So it's easy to see here. So why didn't I just draw it that way? Because here's what you see on the car, if you're lucky. Right, this would be a connector. There's your switch, 2 wires going to it. That's what you see on the car. And you need to be able to visualize what I drew previously and be able to dissect that circuit and figure out what you're working on without a wiring diagram. I'm not saying you should not use a wiring diagram. I'm just saying that that would be something that will save you time and make you more accurate as well. Back it up with a wiring diagram. There's also electronic designs, which we're going to talk about later today, that cannot be identified using a wiring diagram. You have to do voltmeter checks to identify it. Okay? The example there where we're going is this being the engine computer and then this being a crank sensor, and there's 3 wires that go between the two, and the diagram doesn't give you anything here and it doesn't give you anything there as far as telling you what your circuit is and design. So the wiring diagram is useless on what I call an electronic switch input. But can we still identify circuit design? We can with a voltmeter. Unplug the sensor, check your signal voltage. If it's high, it's a pull down. If it's low, it's a pull up. Okay, that's where we'll be going later. Identifying crank sensors, cam sensors, certain types of mass airflow sensors, digital signals, communication devices, all following the same rule. I have some case studies where I have a Lexus in here and it's a ignition system, and I'm actually taking an igniter circuit that controls the ignition coil and I'm substituting the signal. First thing I did is I determined my circuit design, and then I took that signal and made the signal that the sensor would make, and I made the coils fire. That kind of stuff's pretty cool when we can do that. So that's more electronic design switch inputs. And that's the pull down visual. Just get used to it. It's going to take practice before you can do it with ease. Just like anything, practice makes perfect. All right, so what's the answer for number 3? Is it the open position or the closed position that identifies it? The closed position. So that is a false statement. They both look the same in the open position. 12 and 0. Okay? Everyone understand that? Repeat question. Switch input makes an analog voltage signal. False. Good. The rest of this is chapter 3 stuff. I think before we move into the pull-up testing, which is where we're going, I want to talk about this. I want to talk about this bypass test a little bit. And I'm not really sure that this Chrysler Hall effect one would be the right one to watch on that. Let me just see what's in this video real quick. All right, so this is a good video, especially for you guys because you're not using a lab scope, and I'm actually teaching how to do this with a voltmeter. We're not going to watch this video in its entirety. We're just pieces of it. I want to emphasize the bypass test, which brought me here. That's why I was thinking this might not be the greatest video for this. Right now, I'm teaching circuit design, how to test it. I also go through, because it's a crank sensor signal, and because the crank sensor pattern looks something like this, that this voltmeter is going to average that signal. And so I go through that in here as well, which is really helpful.
Signal wire, scope negative. We're working on and what you're going to do. Go ahead and crank it again. All right. Crank it again.
See the average? Can you guys see that number? Probably not, huh? That says 0.466. It was like 0.5 something at one point. So between 0.4 and 0.5, this is 0 volts, this is 5 volts. You see the square wave pattern on the screen. Why would the average of a 0.5 volt square wave be 500 millivolts? Look at the high portion compared to the low portion. High and low, high and low. What's the multimeter going to do? It's going to average this. Can you see that my average is longer period of time we're on ground than we are at 5. So where's the average meter reading going to be? Is down here. Okay? Just characteristics of a voltmeter compared to a lab scope. Side note, that wasn't what my intent was coming here, but as I saw that, might as well talk about it. I really want to show you this bypass test. I'm going to take this crank sensor signal and I'm going to create it with a test light and show you that this can be done for circuit integrity type testing. So that was my main focus of going here.
And it's going to vary on the sensor that you're checking. This is a crank sensor. We should be creating an RPM signal. The computer should react and respond to certain outputs that it would respond to with an RPM signal. One of them is going to be the ASD relay, the fuel pump relay are going to turn on and off because the computer sees RPM. Certain solenoids under the hood may click. In some circumstances, you're going to be able to make the vehicle spark. This particular one needs both cam and crank signals at the same time for spark to take place, so I don't expect the coil to fire. But we're looking for a response. So I'm going to do the test, take a listen to the engine first, and then I'll show you what else we can look at. Test light's connected to ground because this is a pull down.
Ah, come on, I was slow on the draw. I was going to ask you that question. Test light's connected to ground, why? Why am I'm trying to do a bypass test. What does the sensor do?
You need to ground it.
Yes, it pulls the signal down. This is a pull down design. You guys can watch this one later, but this is a pull down design sensor. So my test light's connected to ground to create this on-off signal. And that's what the text says here. Back to my book real quick. Disconnect the switch and touch on and off the signal wire. I'm reading right here. Disconnect the switch and touch on and off the signal wire harness side with a test light to what? To what? To ground. When we're working on pull-down design circuits, that's what we're doing. We're creating that signal with a test light to ground. What type of test light should we use here? I don't know. I'm going to try to spell this. Yeah, it's an incandescent. Do not use an LED. Let's make this easier on myself. No LED. Okay. No, that's not a good. Don't write that in your book. I'll try to spell it. Incandescent. Incandescent light only. Incandescent test light. Thank you. Incandescent test light only. Why? An LED, you won't hurt the LED light. It won't pull it down. It's too high resistance. It's not going to work for this test. Okay? And a suggestion for that, again, I'm gonna plug the premium channel. Got to show you where this stuff is. This is just so you guys know how to navigate. In fact, we just did something different this morning here too. I added this where to start for you guys and navigation on the site. That was much needed. Chapter 2 is where we are. And the one that I want you guys to watch as far as the LED incandescent test light thing, I had pointed this out to you yesterday. That guy right there. This, what's that? You liked it? Pretty decent edits in that one too. I had the camera in the back on the rear wiper showing you the front circuit, and
I like how that popped up in the corner.
yeah. Stuff you learn over the years with edits. But that was a really good video. Thank you, Katie, right?
Yeah.
Thank you, Katie. I agree. One of my favorite ones, as far as kind of summing up what we're talking about, what we're trying to do. Really good video for that. And it really showed how to isolate the circuit and know, say, if you had a bad switch or a bad motor or a bad circuit or module. Really good video for that. Oh, the title of the other video that we're watching is actually, well, the hyperlink's in the book. Oh, it's right here. Just type in Chrysler Hall effect testing, right, on page 8, chapter 2. Let's make sure I didn't change it. Hold on. Nope, I changed the title. How to test a crank sensor with a voltmeter would be the title of that. Right, but here's the thing. I want to remind you guys that aren't using the electronic version of the book and have, you know, maybe you're thinking you have to type that link in. Remember that if my original video title was this, and that's why I kept the title of that, if you type that in to the YouTube search box under my channel, this same video will show up. So if I made any changes, let's be clear, if I made any changes to titles, and I kept the old title in either the description or in the tagline of that video, so it would still be able to be pulled up even if the title changed. All right, then the bypass test coming up with an incandescent light. Before I do that, as I was looking at my premium list, I want to point something out to you guys again. This is a really good lecture on this too. And so I want to remind you guys that even though you're sitting through the class right now and we're going over this chapter, you might think that, you know, I don't need to go back and watch some of these other ones. You would be mistaken. I cover things differently with each class. I recorded things differently, different examples. And this bypass testing, LED versus incandescent test light, really good one for what we're talking about here. Chapter 2, one of my favorites. Chapter 2 and Chapter 3, I told you guys, are my favorites. All right, let's watch this bypass test. The lead into this, so we don't have to watch it here. You can watch it yourselves later. On this particular car, we need both cam and crank signals simultaneously for me to get an RPM signal on the scan tool. I need 2. So to do the bypass test, I have the crank sensor unplugged, and I show the test light on and off the signal wire first, and I don't get an RPM signal. But when I crank it over and now provide the computer with a cam signal, while I'm triggering the crank, I can make the computer show me an RPM. Okay, that's what we're about to do. Let's take a step back for a second. If I'm doing a switch input bypass test, which is what I'm doing, it's a Hall effect in this case, what am I looking for? I'm doing a bypass test. How do you know if the test worked? What am I looking for?
You're looking for it to do whatever the sensor's supposed to.
Correct. Depends on the circuit.
So if you're messing with the throttle body, you want it to like rev up or...
Yes, exactly. I can't think of a scenario where the throttle body, but you're absolutely correct. I was thinking one, Bryce had mentioned cruise control earlier. If you were checking a cruise control, say, set or Excel switch. You guys know what I'm talking about? You have your Excel, then you have your decel or coast, right? Let's say that your cruise control set button wasn't working and you're looking at troubleshooting it and you're going to do a bypass test. What are you looking at to know if the bypass test worked?
See if it says on and off.
On what?
Like scan tool.
Scan tool. Yep. On a data PID on the scan tool, I'm looking at cruise control. It says set and it says off. I do take my test light, touch on the circuit. What does it do? It says on. And how's my wiring? How's my computer all good and that focus on the switch then?
But how are you gonna, like with a cruise control? Some of them they won't set unless you're over like 20 miles an hour.
They won't set, but the data PID will change.
Oh, well.
Yes, it will. That's a good point. You guys hear the question or comment was some of them won't set unless you're driving half mile per hour. Correct. but the data parameter will still change. And you can do it sitting in the shop. Okay? In the case of a crank sensor, yes, Bryce?
I was just kind of curious, so you say like even if certain things can't be set, the data pad will still show like say you try to command the AC compressor to engage.
Yes.
And
it says,
if the AC
yeah.
compressor is not working, you'll still see a pad
Yep.
saying the command to be on.
Correct.
Okay.
Yeah, and that's a little bit different. So the comment was about an AC system problem and using a data parameter where you select AC and then you see on the scan tool it says yes, but the AC clutch still isn't coming on. A little bit different scenario than what we're talking about, but yes, you will still see that command, and that command doesn't tell you that the clutch is actually on. Just, even if it says AC clutch and it says yes, and then you go under the hood and there's no power going to the clutch, you have to remember that you're looking at what the computer wants, not necessarily what the computer is getting. Yeah, so that's more of an output side that you had just mentioned, Bryce, and we're talking about the input side. Now, if we're talking about an AC request signal, that's a little bit different. It would say AC request, yes or no, and that would be solely based off of the button on your dash that says AC. So that would be the input side. But the one I think that you'd mentioned when it says AC clutch, yes or no, that's more of a command than it is an input. That's just like, here's another example of that, and we'll get more into this too on the output side. But let's say you have a fuel injector that has a pulse width reading on the scan tool. It says 2 milliseconds. Does that mean that fuel injector is firing? No, it does not. It just means that's what the computer wants the pulse width to be at, and you're looking at a command, not necessarily what the injector is doing. We could have a wiring problem to that injector. We could have a restricted injector, and we're not getting the fuel that we need, even though the command is proper and correct. So some scan data stuff there. This is what we're doing here, some scan data stuff. I'm going to do a bypass test on a system that will not react to anything I do with the crank sensor alone. My timestamp is 13. I want to go back to that picture where I'm showing, I'll show you why it won't react. The average voltage one that I just showed you guys. This guy right here.
Go 200 millis. All right.
Okay, okay, right there, hold on.
Go ahead and crank it again. All right.
Why would the computer not be able to use this signal alone? Think you can answer that?
Because it might be like a protective device, so that way if it's out of time, it's not being cranked again, never destroy itself.
Crank and cam, this being my PCM, and then we're going to control spark. And on this design, I don't remember if this was distributor or not. They do, but I need my cam signal. And my question really is, why is this signal not enough for the computer to interpret proper RPM, spark, and injection pulse? Let's just keep this simple. I don't mean to disregard what you said. You want to say that again, just so I...
It's like, it could possibly be like a protective device, so that way if the engine is out of time, it doesn't bend rods and destroy itself.
I'm sure some of that logic's in there, but that's primarily not why we would need both signals. What this would have to do with is coordination of the timing, as our valve timing, our spark timing. And on this design, I believe that this was a waste spark system, but I'm not 100%. This could actually be a distributor system. This was a Jeep, and I'd be able to tell if I go back. But let's just, for argument purpose, forget the vehicle and the variables, and if this is a distributor engine, that this should be enough for me to have spark. So each of these pulses would represent a cylinder near top dead center or at top dead center. If it was a distributor design, we should have spark. But if it's a distributor list and it's a waste spark where we have cylinder pairings, or even coil over plug, all I know is that a cylinder is coming up to top dead center. I don't know which one. So that was the point I was trying to make. There is no sync signal in here to tell the computer where to start counting. Remember how we synced our relative compression pattern, and we didn't know what cylinder was what until we put in a second channel and grabbed something to synchronize it with. So that's what we're talking about here. Is crank sensor alone is not enough, and that's the point I'm trying to make. I'm trying to make the computer react to what I'm doing with a test light, and it's not enough information. I need the sync, and what I did to make the test work is I cranked it so I was providing the cam signal, and then I did the bypass and it worked. I admit this is probably not the best video to introduce the bypass test to you, because it's like I'm teaching you something new, which is the bypass test, and then right away I'm throwing a variable at you with it. Sorry, I could have used a different one. Let's watch the bypass test, and then it'll be more clear, and I'll answer any questions you have.
Pull down design, and I'm just going to touch this test light on and off to my T-pin that's connected to the signal wire on the crank sensor.
Yeah, this is a distributor design.
Okay, test light to ground, touching on and off the signal wire.
It did spark. See, I should watch my videos more often. I haven't seen this in a long time. I don't even need a different car. Sorry. That was the test. This is a distributor design. That was only one coil, so every one of those pulses that we just saw on the crank sensor would do what? What would the computer use that for? Fire the coil, fire the coil, fire the coil, fire the coil. Same coil every time. So did you hear the clicks? What was the clicks? Me touching that circuit, hearing the clicks, and that was spark too. It was relays clicking too, because when the computer receives an RPM signal, it turns the fuel pump relay on. So the other, and I think the auto shutdown on a Chrysler. So the clicking you're hearing is actually relays turning on. Does that in itself tell me that my wiring is good from the sensor to the computer? And let's say that we didn't have an RPM signal before, we didn't have spark, and you're pretty sure it needed a crank sensor, and you wanted to be 100% certain. Do you see where the bypass test comes in now? I take my test light, click, 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 done, circuit's good, didn't have that reaction before. I'm 100% confident now I'm gonna put a sensor in that.
You can do this with any pull down?
Yep. Any pull down circuit, on any year, on any make, and on any model car. And the only problem though would be, what reaction will you get? And are there variables? And I described the variable to you guys inadvertently, thinking that's where we were going with this. I don't think I even show the scan tool data on this. Let me see if I do.
You hear the clicking taking place. I'm going to be quiet so you hear it. Just the fact that you hear that clicking tells you that signal circuit is good. The computer's reacting to it. That's how you do a bypass test on a 5-volt pull-down design Hall effect. The other thing you can do, if maybe you have a circuit that isn't reacting, that you hear nothing changing, is you can use some scan data to help you. And in this case, I have the scanner already connected, and I'm going to focus you in on a couple of data PIDs that we can use. And in this particular case, we're going to use the crank count, which is just to the right of the screen. It says crank count. We're at 12. When I touch this on and off, you're going to see that count change. Okay? Is there a reaction on this circuit?
Did you see that? Do you see the coolant temperature and intake air temperature give me voltage readings? They were at 0, and then I clicked on it, they went to 2.7. That was weird. That shouldn't do that. That shouldn't do that.
Yes, there is. The crank count is...
It's scan data for you. It's a lesson on scan data. You can't always believe scan data, number one, and number two, if the car's not running, some scan data parameters won't update until there's an RPM signal. So what was I doing by exercising the crank sensor circuit is I was providing the computer with an RPM signal. And so those data parameters were just updating at that moment. I can't explain why it would read 0. They shouldn't be, but that's what you were seeing. Mainly, our crank count, you saw that change. So how's my circuit? The whole point here, guys, is circuit integrity testing. Looking for a reaction and saying, I'm good, that sensor's faulty, 100% confident, put the $100 in your pocket. Tell the garage, change that part. They say, well, how do I get to that crank sensor? Because these suck on this one. They're on the bell housing. Be like, I don't know, good luck to you. Have a nice day. In the field, when you work in the field, you won't have that luxury. You'll be the one changing the part. Unless you can create this world around yourself, which there shouldn't be a reason you can't moving forward. To be the guy in your shop that just does the troubleshooting and then you have other people do the repair. You kind of delegate. That job is almost non-existent. My friend Tommy, who I always talk about, who works for Volkswagen, what he wants is all the other dealers, within Cochran to send him their cars so he can do that, but he still has to do the repairs. Because usually the guy that can do really good troubleshooting is usually a pretty good wrench too, just from a standpoint of, not necessarily that, because I was thinking of myself, and I get made fun of all the time if I show something mechanical, because I suck at it, because I haven't done it for so long. It's been 18 years since I've wrenched full time. So you want a good video to watch where you can make fun of me, would be watch me do ball joints on my Jeep in my driveway, and I filmed it. I got all kinds of hell for that one. So I was kind of backed up on my thought process there. But what I meant about being a good tech is usually the good drivability guy is very methodical in what he does. But point being is the methodical mind ends up being a good wrench, because comebacks are not part of the game. When you get good at troubleshooting, the reason you got good at troubleshooting is, well, part of being, quote, good is no comebacks. Nobody can be 100%, but point is that usually extends to other work, and what that means is the service manager wants you to do the repair too, because he knows it's going to be done correctly. You see where I was going with that? In other words, we're trying to get away I'm trying to say, can we create an environment where we get away from the repair and we can just point and make some money? I think that's coming. I think even in a garage environment, I think that's coming. I think that job's going to be there, because the way the cars are and how technical they are, you need that one mind that can handle that part and then delegate to the other techs in the shop on what to do and how to fix it. This field's changing more rapidly than I've ever seen it. And that's why I told you guys, like, what I'm teaching you is foundational information. Like this subject in particular, you can see that it's an electrical design that we just learned that we can apply to anything. From a 1980 vehicle where they first started using computers, or 1978, all the way up to 2018, you're going to see pull up and pull down circuits.